everyone, good evening. Welcome to today's course. Today's lecture is Professor Chi-Kuei Wang, Department of Geomatic, National Cheng Kung University. Research interest, remote sensing, airborne laser scanner, terrestrial laser scanner, ocean color, spatial statistics. Okay, first one, please go ahead.
All right. Okay. All right. So good afternoon, everyone. So welcome to Introduction to LiDAR. My name is Chi-Kuei Wang. I'm from National Cheng Kung University. You can reach me at this email if you have any question. Feel free to send me email. All right. So for today's syllabus, so in the first part, I will introduce the laser ranging principles. And later on, I will talk about three kinds of LiDAR. So the first is the ground-based LiDAR, which usually, nowadays, sometimes called terrestrial laser scanner, TLS. And the second kind is airborne LiDAR, nowadays more often called airborne laser scanner. And the last is mobile laser scanner. And for these three kinds of LiDAR, I will show you some examples, so application examples, so you can see how useful they are for your own applications. All right, so the first is LiDAR. This term, LiDAR, L-I-D-A-R, it stands for light detection and ranging. And the light here, okay, let me get my laser pointer. The light here actually means laser. So that's why in my previous page, it's there this term keeps showing up, laser, laser, and laser. Okay, so the light is laser. Okay, so now let's talk about laser ranging. There are two kinds of laser ranging techniques here. So the first is pulse ranging, sometimes called time of flight. The second is phase difference ranging, sometimes called continuous wave method. Okay, so the figure on the right shows the setup of the system and its relation to the object. So let me draw this. So this whole thing, it's actually the scanner. Okay, sorry for the bad drawing. And this is the object surface. Okay, so this is object surface. So the laser light goes out and return back. And then, so this is the signal being transmitted. This is the signal being received, okay, for the ranging, pulse ranging system, okay? And for the phase ranging system, sorry for the trouble with my mouse. For the phase ranging system, okay, wait a minute, okay, so this is the scanner. Again, this is the object. So again, it looks like on the outside, the laser being transmitted and the laser comes back. But something's different is in the inside. This is the signal being transmitted and this is the signal being received, okay? So it's the inside is different. Outside, it looks exactly the same. The laser is being transmitted and the laser is being received, okay? All right, so let's talk about the first kind, the laser, the time of flight system. Okay, okay. Let me get back to the time of flight system, sometimes short for TOF system. So the range that we measure. So the range is from the laser to the object. This is called the range, okay? Here's the range. So how do we measure the range? we send the laser pulse to, and we wait for it to come back. So we actually measure the time interval. We actually measure the time interval of the pulse going from the LiDAR to the object and comes back. So this is the time we measure. Okay, now we actually know the speed of light. Here I use a fancy term called electromagnetic radiation. This is just light, okay, the laser light. So we know the speed of light here, and we can measure the time here. So we know, and we divide it by 2 because it is a round trip. The trip goes to, and the trip comes back. So it's a round trip. So then this is why we have a 2 in the denominator. Okay, so then I like to, so the speed of electromagnetic radiation, so the speed of light. So the speed of light, usually when it is in vacuum, okay, sorry for the trouble with my mouse, 3 times 10 to the 8th meters per second, okay? So that is the speed of light, usually, that's the term, okay? So, and so you can imagine, even though the time, usually we say the speed of light is very fast, but it is still countable, okay, with this number. So you can imagine the time for the light, going from here to there and comes back, it's very short. So we just need to measure that time, and then we can know the range. All right. Okay. So then the other kind is the continuous wave method. All right. So this is a little bit tricky. This figure is a little bit tricky. Here we have the transmitter. Okay. And here this B is actually the object surface. Okay. So for continuous wave, this means we turn on the laser, and it's continuous going out. The light energy is continuous go out. We don't close it as a pulse. Okay, we just keep turning on. So now there's a trick we can do is we put the phase information in the laser light. Okay, so we put the phase information in the laser light. So if we can put a sine wave in the laser light, so we will know what's the phase it's going to travel, okay, to the object. All right. So then the problem is, how do we know the phase it returns back to the detector? Okay. So here's the trick. So this is the A, is where we are. We just extend the same range A here. Okay, so this is R. Okay, we extend further with another R. Okay, sorry for the trouble with my mouse. Okay, so we extend it furthermore. So then we can continue with this phase figure. Okay, by continuously going there. So this is where we will know what is the resultant phase when the signal comes back to the receiver. Okay, so this is just a trick. Okay, so then for this example here, okay, so for this example here, so now we can understand the phase difference for the received signal compared to the transmitted signal. Okay. Okay, so now let's show more of the math. The fundamental equation is the same. The fundamental equation is the same. the range we want to measure, equals the speed of light times the TL is the traveling time here, okay, traveling time divided by 2. So this is exactly the same as the time of flight method, okay? The only difference is how we measure this TL, okay? So now we use this example for an object within one wavelength, okay? So because in this method we only measure the phase difference, okay? We only measure the phase difference. We don't know how many wavelengths it has experienced, okay? So we only know the phase difference, and this is the only thing we measure. We only measure the phase difference, all right? So then there's this equation. So we know because we send out sine wave, okay? For a sine wave, it has a period of t, and it will experience 2 pi phase, right? Okay. And then, so because we can measure the phase difference is phi, okay? Then we should be able to know how much time it has experienced, okay? So that is the equation we will use to calculate how much time it has experienced for the laser goes out to the objects and goes back to the receiver. All right. So with this equation, now we do a little bit math. We move this t to the numerator. Okay. So then we have the TL, and we put the TL into here. Okay. So then we have this new equation in here. Okay, so we have this new equation, and we just rearrange the terms. So make the term like this. Okay, and there's one thing here. The speed of light times the t is the period. Okay, so it becomes the wavelength of my wave. Okay, it becomes this is the wavelength. Okay, in terms of distance, that's my wavelength. In terms of time, that's my period. Okay, so the numerator becomes lambda. All right, so that's the final equation we get here. Okay, now because we can design the wave we want to measure this, okay, the wavelength. We can design the wavelength. We want to measure the distance, okay? So we know the value of lambda, okay? And 4 pi is just a constant. Now we only need to measure the phase difference, phi, all right? So then we know the distance, okay? Hopefully this is so far okay, all right? So how do we put this equation to real use in practice? Okay, because as we all know, the real distance, it must have experienced several wavelengths. So how do we tackle this multiple wavelengths issue? All right, this is one of the system, the commercial system. Okay, so instead of using one single wavelength to do the measurement, it uses 3 different wavelengths. Okay, so with the longest wavelength here, okay, so there's this the object is here. So with the longest wavelength, it can determine it is in this region. Okay, so within this region, it has the second wavelength, the shorter wavelength. So it can determine more accurately where it is. And then with the smallest, with the shortest wavelength, it can more accurately determine the range of this location. Okay. There's a thing I didn't say is that the longer the wavelengths, the worse the ranging accuracy you have. So that's why we want to have a shorter wavelength to achieve better ranging accuracy. Okay? All right. So, yeah. So, if you have any question, feel free to type your question in the text in the chat area. I think I should be able to see it. If I cannot see it, just let me know. Let me see. Okay. Yeah, I think I should be able to see it. Okay, let me see. Wait a minute. I think, yeah, I think I'll be able to see it. Okay, so feel free to type your question here. I'm happy to answer the questions. All right. Okay, so I'll keep continue with some introduction with the LiDAR. Okay, now here I give you examples of the ground-based LiDAR. So the ground-based LiDAR, the terrestrial laser scanner. So the ground-based LiDAR, as the name suggests, it is on the ground. So usually it sits on a tripod. Okay, it sits on a tripod. Okay, and this is where the laser being transmitted, and it rotates. The whole system will rotate like this. Okay, and the mirror rotate like this. Okay, so just it pretty much all system they rotate. Okay, and depending on how the way they rotate, the first one being a panorama scanner, so it scans everywhere. Okay, not only it scans the side, it also scans the top. Okay, and the extreme opposite of a panorama scanner is the camera scanner. Okay, the camera scanner is something like this. So like this one, it's a fixed system. For this yellow thing, it's a fixed system. It only scans everything in front of it. Okay, so it's like a camera. And in between, we have hybrid scanner. So it scans a certain range around it. I have to say, for what I know, most of the system, they are in this hybrid scanner or the panorama scanner. Okay, the camera scanner this kind, nowadays is not very popular. Okay, and then you may ask why we have a hybrid system. How come we don't scan the top? That is because this kind of system, because sometimes we like to have color in the point clouds. And because laser is only one single wavelength, okay, I think you'll have experience with the laser pointer when you use a PowerPoint to talk, right? You have a laser pointer. And the laser pointer is usually a green laser or a red laser, okay? That's one single wavelength, all right? So for the laser scanners, they also use one single wavelength. That means it doesn't have color. The color has to come from the photo. Okay, so that's why we sometimes want to put a camera on top of it. Okay, so when we put a camera on top of it, then we cannot scan top. Okay, so that's why we have the hybrid scanner. All right. Okay. Sorry. Sorry, wait a minute. Okay, so this is an example when we have a ground-based LiDAR. So on the left-hand side, is the point cloud with this site, such as this. On the right-hand side, as the photo, is this complex site. Okay, so we can use the terrestrial laser scanners to scan it. All right, so we can know all the exact 3D coordinates of everything, and we get the point clouds. Okay, so then the color, this color comes from the camera. So that's why we want the color, because it helps us to understand the data we are looking at. Okay, so with this example, I think we can appreciate why we want to scan in this complex scenario, in this scene, in this site, because it is a very tight space, and still we want to put a heavy thing in this site. So we need a crane. We need a crane to help with this heavy lifting, and we really need to know what's the space, how much of the space is available in this site for the crane to operate in here. Okay. All right. And so the other example is this. So with one man doing the job, so we put this scanner on tripod. So you scan in this at this location. Actually, there actually are other locations being scanned as well. So the whole thing looks complete. So with this, and also the camera is used in this in the system. So that's why it has colors. Okay, that's why it has colors. So you can see in this very small intersection, you have all the colors with the facade colors of all the buildings, and also the light poles here and there, all the light poles. Okay, so it can be done with a single person. Okay, now here I would like to talk about this intensity value here. Okay, so it's, I think you understand that we can, because this is laser being transmitted out, comes back, and with the accurate measurement of the range and also the accurate measurement of the angle, so you know where the laser being transmitted comes back. So the XYZ sounds trivial, and so the last thing is the intensity. Okay, so this intensity, I would like to explain that because the laser light is being transmitted out and comes back. So this is exactly in the remote sensing, we talk about the reflectance. Okay, so all the material surfaces, they have reflectance at different wavelengths. So same as this. So for laser, for the laser, the surface, they all have different reflectance value for different laser wavelengths. So this is the a photo, a building in our campus. This is a photo, and you see there are different materials. So they show up different intensity value. So the white color meaning it's brighter, and it means the reflectance is higher. So visually, this material seems like a dark red, but actually it's quite reflective in the laser wavelengths. Okay, and this material looks bright in the color, in the true color, but it is not as reflective in the laser wavelengths. Okay. Oh, by the way, sorry, I forgot to mention that for the laser scanners, usually for the laser scanners, they are infrared wavelengths. Okay. So the behavior, the reflectance value in the near infrared is somewhat different than what we see in the visible range. Okay, and another example is this. So this is a river and this is a dam. So this concrete surface, the concrete surface of a dam. So this concrete surface is highly reflective. Okay, and all the vegetations and the bare surfaces, soil surfaces. Okay, so we can use the intensity to differentiate different materials. Okay. All right. Okay. So far this is ground-based laser scanners. Any questions? Let me check my chat room. Okay. So far no questions. All right. Feel free to ask. Okay. So now I would like to talk about the airborne laser scanning system. Okay. So now we have the laser scanner. We put the laser scanner on the airplane. Okay. And also on the airplane, we put a GPS. We put a GPS here. And also we put the IMU here. Okay. The purpose of this GPS is to know where the location of the airplane, and because we want to know where does the laser being fired out from the airplane, okay? And for the IMU, so for the IMU is we want to know the attitude of the airplane. The attitude meaning, can you see my, can you see me? In my, sorry. Okay, so this is like an airplane. So you supposed to be able to see where does it turn. The location is the same, but you like to know where does it turn and what's this attitude, okay? Because if the wind is blowing from one direction, that you don't fly airplane like this, okay? I'm sorry. Let me draw. Let me try to draw, okay? Okay, so this is the airplane. It flies to here, okay? So you may expect it to fly like that, but actually you will have wind blowing from this direction. So if you have wind blowing from this direction, you would like to fly your airplane this direction. So it still fly like that, okay? The trace is still like that, okay? But the attitude is not as expected. It is not like driving a car, okay? So you have to fly against the wind, all right? So that's why the IMU is important, okay? All right. Okay, so you would like to have a high precision GPS for the XYZ, the sensor location, and you would like to have the IMU, inertial measurement unit, to measure the angular orientation of the sensor with respect to the ground. And also, we just put a laser pulsing system on the airplane. Okay, in here, I think I want to clarify this. The pulsing, they do not send several pulses at the same time. The pulses are being sent out one by one by one by one. Okay, so it sends out one by one by one. Okay, all right. And then there's this other thing. There's a ground GPS here. This is a GPS base station. Okay, I think for some of you, if you know the differential idea of GPS, you may think, oh, this is where we want to use a scenario. Here we'd like to use a differential scenario. Okay, we'd like to use the differential solution of the GPS so we get a better accuracy. Yes, the answer is that it's correct. And there's actually another consideration. If you are working on a larger project, which you want to measure the geometry, if you want to map a larger area of your country, you would definitely need, or you definitely want a ground-based a GPS base here, because that will help you to solve the local coordinate system problem. Okay, the GPS, the reading of the GPS by default, right? By default, it is the WGS84. Okay, and I think for each of your country, you have local coordinate system. That will become a big problem if you want to bring the WGS84 to your local coordinate system. Okay, you need to do the coordinate transformation, and that is not uniform everywhere in your country. Okay, even for Taiwan, for such a relatively small island, this transformation is not uniform. Okay, so we heavily rely on the ground GPS, so it is easier to conduct nationwide mapping using the airborne laser scanning. Okay, and here I have a term called direct georeferencing. That means the way we obtain the 3D measurement of the points is by knowing the position of the GPS, okay, by knowing the reading of the GPS, and by knowing the orientation of my airplane, and by knowing where the laser fires out, okay, and also the range it transmits, okay. So this is all direct, okay. So this is direct georeferencing, okay. All right. So now here is the example of this is more fundamental of the airborne laser scanning system. Watch carefully for the right. For the left. Is the laser is being transmitted from the airplane to the ground for a vegetated area. So we sent the laser. Okay. Look at the waveform first. Okay. Look at the waveform first. So we send out a pulse, and this is the temporal history of the pulse coming back. Okay, because this laser will hit the top of the surface, and some energy get reflected back from the canopy, from the vegetation canopy. It could reflect it from the leaf, or it could reflect it from the branches. Okay, and because you can see the laser footprint has a certain size, and there are spacings between leaves and branches. So for the energy being reflected, it comes back to the airplane, to the system. But for those not being reflected, it will keep going downward. Okay, it will keep going downward to the floor. So it will keep going down until it hits some other structures, and that energy will be reflected back. Okay, or it keep going down to the bush, so it being reflected. And finally, because there's no gaps on the ground, so all energy will be reflected from the ground. Okay, so this is the complete temporal history of the signal being transmitted to the ground when it first hits the canopy and hits some other canopies, and then finally hits the ground. Okay, now, so on the left-hand side, this is discrete return. Okay, because engineering reason, is that if we want to record the full history, the full temporal history of the signal, that will take a lot of memory of our hard drive. Okay, so technically or engineering, in terms of engineering, we only want the first return, okay, because we think the first return is the top of the canopy, so we keep it. And for the second return, if it exists, so that means something in the canopy, so that's the second return. And then this is the last return, so this is the last return. Last return means it's the ground. So this, by saving only limited numbers of returns, this saves quite a lot of memory space. Okay, so that's why a lot of the time we like to only save discrete data. Okay, discrete returns. Okay, so as you can see, usually the data looks like this. So this is a forest area. You can tell there are forest canopy, single trees out this area, and this is a dense vegetation out this area. Okay, if you cut a profile through it, and you will see the penetration is very good. It's we can see the ground, and also we see the vegetation. Okay, so this is a good example. Okay, now here I show some of the examples of the airborne laser scanners. There's only one thing you need to remember, or you need to know, is that because we say you just need a GPS, an IMU, and the laser scanner, and we didn't say what geometry requirement you need. So then different company has different creativity. So people are actually being very creative. So the airborne laser scanners, they come with different size and different configurations. Okay, so that's that. Okay, now then I'd like to give you some examples with the airborne LiDAR. So then for the LiDAR, airborne LiDAR data analysis and applications, and usually the raw LiDAR data, they are just visualized as a point cloud. Okay, so such as this one. Okay, it's like a point cloud, and they have intensity. So because it's being reflected from the leaf, from the branch, or from the building, from the road, or from the ground. Okay, so it has the reflectance value. Usually in LiDAR, we call it intensity. Okay, and that's in three-dimensional. And so before we can further process it for an analysis, so this LiDAR data points, point clouds, usually we say point clouds, we usually need to classify them to isolate them into different types of features. Okay, and usually, of course, they exist automatic algorithms to help you to classify vegetation, to help you classify ground, to help you classify buildings. But to keep in mind, the automation is not, it's just to help us to cut our time, cut our working time, but it's not guaranteed to give you satisfactory result. Usually, from my experience, it involves some manual processing or manual editing in the whole process. Okay. All right. So here I give you more example of the airborne LiDAR data. So this is an example from urban area. Okay. So with a building like this, let's look at this in this way. And for another building, we can see it like this way. Okay. So in here, I hope you can see that the LiDAR points, because they're just points, in this LiDAR point, it doesn't have the information of which is front, which is back. Okay, so with all the points showing, we can actually see through the building, and that sometimes become confusing. All right, because you are seeing the top of the surface and the bottom or the back of the surface at the same time. So that's sometimes being quite confusing. All right, and the other thing is because we fly the LiDAR. Okay, we fly the LiDAR. Later on, we'll show more examples. We fly the LiDAR. It scans. Okay, actually, I can explain a little bit here. Because it scans. It only scans in the from left to right and from right to left. So it only scans in one direction. So it may sometimes, especially in the urban area, it may miss a part of a side of the building. Okay, so then you may be wondering, why do I want this kind of data? Well, it depends on why do you want to scan the whole area. A lot of the time, actually, we just want to know the elevation of the whole area. Okay, a lot of the time we actually don't want to know the elevation on the side. Okay, for example, we only want to know how tall are the buildings in a city. We don't care the measurements on the side. So this is actually okay. All right. So in terms of data-wise, it's actually okay. All right. Okay. So, well, the other thing is with this data, with these points, they all look good on the left figure, but actually they become somewhat confusing on the right if you look closer. Okay, so this is actually a kind of problem with LiDAR point clouds. Okay, so I'll give you more example. So again, this left figure I've showed before is the vegetated area. So you actually see the ground, and you see the single trees here, and you see a dense vegetation here. On the right-hand side, it shows it's orthophoto. Okay, on the right-hand side, it's the orthophoto. Actually, this orthophoto gives you more information because it's an image, and we are used to look at image, so we can see we can quickly recognize this is dense vegetation. These are single trees. Okay, so we definitely when we collect airborne LiDAR, any kind of LiDAR, we definitely want the color image as well. It helps a lot with interpreting the LiDAR data. Okay. Okay. So here I give you one more example of this. Okay. So on the right-hand side, I think it's very clear. You see this is two rivers. One river is here, and the other river is here. Okay, this river is full of water. This river is relatively dry, so it has this channel. Okay, it's like that. And you see two bridges. One bridge is here, the other bridge is here. Okay, and you also see buildings. Okay, so this is what we can tell from this photo, from this orthophoto. Okay, so the airborne LiDAR, based on what you want to visualize, actually a lot of time based on what you want to visualize. Okay, because human eye, we can only see a limited number of colors to tell the difference. Okay, So in here, I like to maximize the difference in the sandbar. Okay, this is something I did before. I like to minimize the difference in the sandbar. So in here, what I can see is this part of river is low. Okay, this part of the sandbar is high. Okay, so with this good measurement, I can tell this. With this measurement, I can tell this. All right, and also I can also measure this bridge and the other bridge as well. Okay, so here I also cut a profile through the bridge here. So here's the result. So let me zoom in. Let me see. Oh, here. Okay, so you can see this is the bridge surface, and those are the light poles. Okay, so I can also measure the light poles. Okay, and this is the sandbar. This is the sandbar. This is the water area. This is the other water area. Okay, and I hope you can see that even though in the ortho photo, it's just the water area, but the LiDAR measurement actually shows this water area is actually higher than this water area. Okay, even though this is in the same channel, this is in the same river. Okay, this is in the same river, but this side of water is higher than this side of water. Okay, so this can be measured from the airborne LiDAR. Okay, and the other interesting thing is this supporting structures pillar, the the pillar of the bridges. Okay, you actually don't see the pillar. You actually don't see the pillar underneath the bridge, but because we are scanning. Oh, I'm sorry. Let me go back a little bit. Because we are doing the scanning. Okay, we're doing the scanning. So if let me draw a little bit here. So if I have my bridge here, my pillars here, so I can actually scan. Well, if my flight design is appropriate, I can see beneath this bridge. I can see the pillar underneath the bridge. Okay. Okay. So this is why I have this. I can see the pillar. Okay. And so the other side is just this flat river surface. Okay. All right. Okay. So far, any question? Okay. Let's see. When we want. Okay. So let me try to answer this question from Kwak An. Is that when we want LiDAR to detect the level of water in river, can the results be affected by transparent of water? Okay. No. The answer is no. Because we just measure the signal. Even though this example is the, sorry, let me change. For this, even though this example is for terrestrial, but the principle is the same for every kind of LiDAR. All right. So it's just laser transmitted to the water surface and it comes back. Okay. Now the thing is, why do you have the reflectance of the water surface? Okay, this actually is the. Let me try to type here. Okay, let me try to type. Okay, there's something called Fresnel reflectance. Okay, so for the water surface, you have Fresnel reflectance. Okay, and for that, the transparency doesn't affect anything. Okay, but the transparency will affect the other thing. But I'm not going to talk about that today. The other thing is there's something called bathymetric LiDAR. Sorry, let me. There's another kind of LiDAR called bathymetry LiDAR. If you guys know this fancy word, bathymetry, that's called water depths. Okay, bathymetry LiDAR, it can measure the depths from the air. Okay, so the transparency affects the efficiency of the LiDAR measuring the water depths. Okay, so apparently, the clearer the water, the better the transparency, the better the efficiency this LiDAR has. But this is, but just so you know, the bathymetry LiDAR is more for coastal application. Okay, you don't use it for open ocean. You just use for coastal, where the ship is dangerous to get to. Okay. All right. The other is, can we use the airborne LiDAR on ice caps or icebergs? Of course, yes, yes. Because on the ice caps and icebergs, because it's covered by snow. Okay, of course it's ice, but it's actually covered by snow. Snow has very high reflectance, so it's actually very good to use the airborne LiDAR to measure the elevations or the geometry of the ice caps and icebergs. Okay. Actually, there's the satellite called IceSat. It is LiDAR on the satellite. Okay. So actually, there's also this LiDAR on the satellite to measure ice. Okay. All right. I think later I will take a break at 5 o'clock. All right. So let's just continue. Okay, so here I give you more example about the airborne LiDAR of an urban setting. This is actually our campus, a part of our campus. All right. So this area is our campus. This is the train station. There's this there's a fancy hotel, or actually a department store and a fancy hotel here nearby our campus. So you actually welcome to visit us when the situation gets better. So you can see it's actually you can actually see the building, the trees. Okay, you can actually see the trees here and there. You can actually see some buildings. Okay, but as you can see, it's difficult to interpret airborne LiDAR data directly as this. Okay, so one kind of visualization technique is to link all the points to make it surface. So you can see now some of the buildings. This is actually a student stadium. So it becomes easy to read, easy to interpret, and some of the department buildings here and there, and very strange shape of building, and this tall building becomes this. Okay, so actually it becomes more readable if we visualize it properly. Okay, and here I like to give you a direct comparison of LiDAR versus photo. Okay, this is aerial photo. Okay, this is actually 3D, a 3D model with photo being meshed onto it. Okay, so you can see this fancy hotel and the department store and this strange shaped building and the stadium. Okay, you can recognize that in here. All right, but this information, okay, this field and track, this tennis court or baseball court, you cannot recognize it. Okay, so I have to say, airborne LiDAR is particularly useful when you want to measure the 3D. Okay, it is not so advantage to measure such a flat feature like this. Okay. Okay, but don't worry, I'll tell you what the airborne LiDAR is particularly used for. All right. Okay, now, so because the ability to detect multiple returns, okay, from the plant canopy and the ground surface is one of the most revolutionary aspects of LiDAR remote sensing. Okay, or so we need to recap this multiple returns. Okay, come back to this. This multiple return, okay, or you can just think of this multiple return. This is revolutionary in terms of LiDAR remote sensing. Okay, so we can use it to create the DEM, okay, by using the last return of the pulse, and we can use the classification functions, and we can characterize trees, shrubs, and other vegetations. Okay, so here I show you the DEM. Okay, so the final product of airborne laser scanner is usually DEM. Okay, don't worry about it. I'll explain what DEM is later. Okay, so it's just figure. So you can see this is a small part of Taiwan. See, a small part of Taiwan. So this is the river. We have the sand dune, and this is the roads, and we have the farm fields, and you see this intentionally. We cut off the bridge. Okay, because of the requirement of the DEM. Okay, so it's very highly detailed. Okay, and another part of Taiwan now just show in black and white. This is all elevation. Okay, this is just all elevation. Okay, so this is Yilan, actually. This is Yilan. This whole area is a delta. Okay, and we see all the mountains here. Okay, and this is another area. So we see a lot of very highly detailed surfaces of this area. Okay, and this actually is a volcano. It's a volcano. In Taiwan, we have just one volcano in north of Taipei. Okay. All right. So I'll briefly explain what DEM and DSM is, and we will take a 10 minutes break. Okay. So here I'll explain what is DEM, DSM from the point cloud. Okay, from the point cloud. So here we have an airplane flying over. So then all the points are being populated on the surface. Okay, so you have the vegetation, you have the tree, as before, on the top of the canopy, you have some points. In the middle, you have other points. On the ground, you have more. And this is just a pile of dirt or some elevated terrain. So the LiDAR doesn't penetrate. Okay, so that's why the point is on top of it. And this is some building, other building. So all the points are on the surface. Okay, so these are called point clouds. And then in the process, we want to classify it. So the first, we want to classify the ground points. Okay, so this is the ground points. Okay, these are the ground points. Okay, these are the ground points. Okay, I want to correct this first. This is building. Okay, so the DEM. Okay, I'm sorry. The DEM stands for Digital Elevation Model. Okay, so it describes the model, elevation model that links all the ground. Okay, so that means this pile of dirt can be removed anytime, right? And this building was not there; it could be taken down. Same as this building. Okay, human can do something to it. Okay, and this vegetation, it can grow, it can be cut down, so it can change. So if we link all the points together, all right, so this is the DEM. So this is the DEM. So this surface is an elevated surface. This is a natural elevated surface. Okay, this is something we call bare surface. Okay, and for the local high points, so we find all the local high points. All right, so we link all the local high points and it becomes DSM. All right, so the digital surface model. Okay, all right. Okay, I would like to take a 10 minutes break here. Okay, please come back in 10 minutes. I'll see you in 10 minutes. All right. If you have questions, feel free to ask. I'll take a look at them. All right. Okay. All right. Okay. All right. Let me answer some of the questions here. So, Faiza. So the question from Faiza is how to segregate ground points from surface points. Okay. I think later on I will talk just a little bit about it. But I think the quick question for you is there are a lot of literatures talking about how to separate the ground points from the rest of the point. Okay. But I think the easier answer for you is the commercial softwares, or sometimes the free softwares. They offer these functions, and you can just use that. But my suggestion is actually not only you use those softwares or use functions to separate or to extract ground points. You also have to have a good interactive software for you to visualize the data and to correct the data, to correct the classification. Okay, I'm not talking about this today, but there are some softwares that can help you to cut the LiDAR profiles so you can edit the classification. Okay, I think for those of you who may have experience with the image classification or some kind of task like that, you should have the experience that the classification, the automatic classification is not always good. All right, so same thing for LiDAR. So if you want a very good result, such as those examples I show you in my slides, then you definitely need some manual editing to make it a very perfect surface. Okay. All right. So for the other question is from Alan. So you're asking about the speed of the airplane. Does it affect? So I think you have two questions. Well, I think even for the first question, it's you're talking about two things. Does the speed of airplane affect the quality of the data? And the second question is, does the altitude of the airplane affect the quality of the data? All right. From my experience, the speed of airplane does not affect the quality of the data. All right. Because usually airplane fly at 80 to 100 knots, as I know in Taiwan. Even for a helicopter, the speed is quite constant. So that's what you get. And the other thing is the distance, because you sometimes will fly higher for many reasons, because maybe you want to cover a larger area. Because you fly higher, then with a certain field of view, you can cover a larger area. So for example, what I'm talking here. So for this scan angle here, for this much scan angle here, the FOV, if you fly higher, right? If you can fly higher with the same FOV, you will cover a much larger area. Okay, sometimes you will do that. All right, but I'll tell you, the higher you fly, the worse your data quality will be. The data quality meaning, I think here you see it's a very tight surface. Okay, you'll see a very tight surface. But if you fly too high, the surface will become like that. Okay, become more noisy. Okay, more noisy. Okay, so you may be wondering, why do I want a more noisy data? Well, depending on your budget. if you don't have enough budget, not only the money, but also the time. So for example, why do you have only limited time? Because it rains a lot. The cloud comes so often. It's just a time frame. You just have limited time frame. So sometimes you just want to fly as quickly as you can. So maybe you want to fly higher. So many considerations, okay? But if you can, don't fly high, all right? From my experience, if you fly high, many bad things will happen, all right? Okay, is it dependent on the kind of laser being used for such activity? Basically, all airborne lasers, they are the same. Well, I have to be political correct because all companies, all manufacturers, they make airborne laser scanner. So they are fundamentally they are the same. Okay, same thing as terrestrial laser scanner. All terrestrial laser scanners, they are equally the same. Okay, so what's the difference? It's just you have a certain kind of airplane. It is better for a certain kind of scanner. Okay, or in terms of your application, you may choose a certain kind of scanner. All right, so it's actually based on your project. All right. Okay, for Marco, are there any accuracy standards for LiDAR data? Yes, there is. I think the one can be most easily found is the USGS LiDAR DEM standard. They have that. In Taiwan, we also have our standard. Our standard is that the DEM has to be 20 meter. In the final DEM, the accuracy is 20 centimeter. In terms of elevation accuracy, it has to be within 20 centimeter accuracy. Okay, 20 centimeter accuracy. Yes. And then for USGS, I forgot the exact number. All right, you can look it up. The USGS has their number. All right. Good. Thanks for your questions. So I'll continue with my slides. Okay, so we talk about the DEM and DSM. All right, so this is an example showing you that. Okay, let me get my. This is an example showing you that those different symbols. Okay, those different symbols. The triangles are the first return, the plus are the second return, and the squares are the third returns. Okay, so you can think. The triangles that are most likely to be present on the top of the canopy, okay, and the plus, they tend to be in the middle of the canopy or somewhere in between, and the squares, they tend more like to be on the ground. But I have to say, this is not guaranteed. Sometimes you can also see that the third return is in the middle of the canopy, okay? But geometrically, you can see you have a continuous ground, okay? So I have to say, this is actually a good example. So if you use the software to process this data, chances are you can get a pretty good result on this to extract the ground points, okay? So if you look more into it, so there are different scenarios. The laser fires down, so it may just directly hit the ground, okay, or it hit the top of the canopy, the second layer, the top of the second canopy, okay, and hit the ground, or it just hit the top of the higher canopy and it stays there. Why? Because it's just so thick. it doesn't penetrate through. When we say penetrate, it doesn't mean it penetrates through the leaf. It actually just passing through the gaps between leaves and the branches. Okay, it doesn't make a hole on the leaf. No, it just passing through the gaps between the medium. Okay, so it can be hitting. Just the chances are it just hit the first hit. It's in the canopy, and the second is still in the canopy. It doesn't reach the ground. Okay, so for other scenarios can happen. Okay, so it actually doesn't guarantee the last return will be on the ground, but we just say the last return is more likely to be on the ground. Okay, so this is all the returns. It's like that. Let me zoom in. So all the returns is like that. So you separate into first return, second return, third return, and fourth return. Okay, so you see the fourth return. Yes, it has the high probability of being the terrain. And the third return also be on the terrain and also has some of the second vegetation. And the second return, it has a lot of vegetation, but also quite a bit of the surface. Okay, and the first return, of course, it has a lot of vegetation, but it also has the terrain information. Okay, so yes. So yes, if you want to extract the ground points, not only you would use the information from the returns, but also you would use the information from the geometry. Okay. All right. So if you have the digital surface model, which is the digital surface model, is like that. You link this one, so you have the digital surface model. If you link the bottom here, this is the bare earth. So you have the DEM, or sometimes people call it DTM. So, but by subtracting the two, you get canopy height model. So you can know the height of each tree if your data is good. Okay, and we use that as for our data. So actually, we use it to find some of the giant trees in Taiwan. Okay, so we have very tall trees in Taiwan, but we don't know how tall exactly they are because it's actually very difficult to visit everywhere in the woods. Okay, so yeah, this one, we try to measure it in the LiDAR data. So they are roughly at 62 to 64 meters high. Okay, they are very giant trees, very tall giant trees in Taiwan. We are very excited with those findings. Okay. Yeah, I'm sorry. I'd like to say more about this. So this is what the LiDAR data is become very useful compared to air photo. For the airborne photograph, you would not get this. Okay, you would not get this because the LiDAR can penetrate through the canopy, so we can measure the canopy. Okay, so this is a very revolutionary result here. Okay, the other thing is we can use the LiDAR to measure some of the volume change, such as this sand beach here. Okay, one thing is that because LiDAR only relies on reflectance. Okay, when the light hits the surface, it reflects. Okay, so for this sandy beach area, it's actually more difficult for photogrammetry. Okay, I know in previous weeks you had photogrammetry. Sandy beach is actually quite challenging for photogrammetry to make 3D model. But for LiDAR, as long as the surface reflects, the 3D model is there. Okay, so this is where the LiDAR data would be useful for. Okay. All right, just a short introduction to the Taiwan LiDAR DEM projects. For our project, for the LiDAR project, nationwide, well, or island-wide project, is that we want to produce 1 meter resolution DEM. We finished our first phase. It was 6 years. We took 6 years, and each year we had 3 to 4 surveying companies. Even though Taiwan is not really wide, not really long, we are actually a very small island. But it took us 6 years: first year, second year, third year, fourth year, fifth year, sixth year, and then for each year we had 3 companies in here, 4 companies in here. So it took us each area there was a company responsible for that. Okay, so we finished the first phase. We are in the middle of the second phase. Actually, we are closing to we almost at the end of our second phase. Okay, and for that we have 2 to 3 surveying companies each year. We have many interfaces. Okay, so you see for each company they only survey a small section of Taiwan. So there are many interfaces. Okay, and also we want to, because our map is our base map. We want to produce base map at 1 to 5,000 scale, such as this. Okay, such as this. So that means we will have 5,374 of that, many of the base maps. So that means we need to cut all the data into smaller parts, but still we need to make sure the borders, they have good match between their neighbor maps. Okay, so it is a very large volume data and several data types, not including the original LiDAR data. Actually, that's a lot of that. And then finally we create DEM data and also the DSM data. All right. Okay, so this is finally looks like this. Okay. All right. Here I'd like to talk a little bit about the flight planning. Because airborne LiDAR is you need to fly the airplane in order to get the data. So this is example for this area. This is how you want to collect the data. So you will have the airplane fly in this direction. Okay. But in reality, when you fly the airplane, you need to understand the airplane doesn't turn like a car. It needs to fly over far away and then come back and make a big turn to come back. So when you think about the airborne LiDAR, you have to also consider the turning. Okay, this is the important thing of this side. You have to consider the turning. Okay, and the other important thing is after you get the data, this is very important, stripe adjustment. Okay, even though we calibrate all the LiDAR before we do the scanning, but there are still things cannot be accounted for in the data. So when you get the data, even though there's a house, there's one building there, but if you fly back and forth 4 times, you will get 4 rooftops. Okay, this is expected for any kind of LiDAR data. All right, so that means you need to do stripe adjustment. So what is stripe adjustment? You would like to minimize the difference between different flight lines. Okay, so this is what you have to do. So how to do it? This is just a fundamental. Okay, I would suggest you to hire a surveying company who can do this for you and make sure they do this. Okay, so the thing is, you will fly the stripe 1, stripe 2, and many stripes, and you will have a cross stripe. Okay, this cross stripe is very important. Okay, it's very important. So, and then because all the stripes, they have overlaps. Okay, so you will find overlapping surfaces overlapping surfaces, and overlapping surfaces. Okay, you will find a lot of overlapping surfaces. And you can minimize the differences between each overlapping surfaces. Okay, once you can do that, it's done. You should have a good LiDAR data. Okay, all right, this is very important. All right, so with good LiDAR data, you can have good results, such as this one. So on the right-hand side, this is our typical hilly terrain in Taiwan. So let me zoom in. So here's a river, upstream river. So it's almost dry, upstream river. And we have road cutting through the slopes. And here are the little yellow things we are drawing. It is this, okay? So this is the dry river, and this is the road, okay? And those are the little things, the yellow things we're drawing. So what we're drawing is this. Because we specifically design our flight line to make the penetration good. So we can see this. We can see this in our data. Okay, we can see this in our data. Okay, we can see this in our data. Very tiny features. Very tiny features. Okay, so what's the importance of this? Because in geology or landslide people, hydrology people, I think we all know this. If there's a river cutting through the slope, we all know the slope is sliding down. Okay, then now the question is, which part of the slope is more dangerous than the other? Okay, so with this, we know on the top, well, this is the geologist told me. With this information, now the geologist can tell these are the more dangerous part. Okay, these are the more dangerous locations to be. So in the future disaster, if future disaster is going to happen, these are the location that's going to happen. All right. Okay. Okay. So with good penetration data, you can see this all well vegetated area, right? Actually, if you can take out the canopy, you see all the road. Okay, they are very small roads actually. They are just very small roads used by farmers. Okay, and well, the other example is from UK. They take out the vegetation so they can see some remnants from mid-century. Okay, this is from maybe some archaeological application of this. And another fun example is from Japan. So this is very well vegetated. If you take it out, then it's a tomb. Okay, a royal tomb. Very clear now. All right. So as I mentioned before, we have one volcano in Taipei. So with this terrain, look like this. Okay, this looks like a river. So it looks like a flat area, and this looks like a volcano. All right. If you take out all the vegetation, now it becomes actually clear. This flat area, it actually gives you the feeling that it was flowing from the volcano. Okay, so that's why with good penetration, with good quality of data, you can see a lot of features from this. Okay. All right, and in here, let me see. I hope you can see this. Okay, I hope you can see this. This is I got from YouTube. You can actually search for this. Okay, it's okay if you don't have voice, if you don't have the sound. This is in South America. So they use LiDAR to see the Maya. Okay, so airborne LiDAR, I think you can see. Okay, and this one is more interesting. This looks like very high resolution. Okay, sorry. Okay, very high resolution. Now flies out. Now it becomes a low resolution. So what they did was they scanned the area. They scanned the area. I'm sorry. They scanned the area with terrestrial laser scanner and registered the data set to the global coordinate system, so it can merge with the airborne LiDAR data. Okay. All right. So this is a very fun example. And the other thing is some other interesting things happening in the airborne LiDAR industry. Is this example? Okay, let me try to find my 44 minutes. Okay, I think this is okay. So what's happening is that on the left, you can see the track. It's uniform size. On the right-hand side, the track is not. Why? Because many of the system, they have fixed field of view. Okay, so the coverage of the laser, the coverage of the stripes is affected by the terrain. So if the terrain is higher, then you cover smaller widths. And if the terrain is lower, you cover wider widths. Okay, and you definitely want to have you actually want to have side overlaps. As I mentioned before, you want to have the stripe adjustment. Okay, so this company is saying with their new technology, they have uniform points on the ground instead of having a narrower coverage at high altitude. Okay, so that's what they are saying. They're promoting this. All right. Okay. Wait a minute. Okay. And this is another company. Let me get to 33 minutes, 33 seconds. Okay. Okay. So what's happening here? Now, instead of having one laser, this company put 2 laser scanners in one system. Okay, so this can be done actually if you have enough budget to buy this actually. All right, so one scan, so it's flying downwards. One scanner is flying this direction. The other is flying is scanning other direction. So as a result, you will see very good data. Okay, very dense data. Okay, and it will cover a lot of angles. That's actually what they want to say. They can cover a lot of angles. Okay, I'm sorry, I missed that part. Let me. Okay, sorry. Let me. Okay. Okay, this is what I want to say. So, with some angle difference, you can get more data. You can more points on your buildings. Okay. All right. Okay. Now I want to talk more about the last kind of LiDAR I want to talk about today is the mobile laser scanner. Mobile laser scanner. Sometimes it's called dynamic terrestrial laser scanner. The reason it's called dynamic terrestrial laser scanner is you can see this. They are the kind of terrestrial scanner you would use, but you put it on a vehicle, so it becomes dynamic. Okay, but I have to say, nowadays, mobile laser scanner is more often used. Okay, so for the system, you can see it drives on the road. If you drive through a tunnel, you can see the tunnel. Okay, you can measure the tunnel. You can measure the shape of the tunnel. You can measure the height of the tunnel. All right. Okay, and many companies make such a system. You can put it on a van or put it on a truck. Okay, of course, it has the GNSS, usually, laser scanner, and have a camera, 360 degrees hemispherical camera. Okay, actually, this one, I think you can tell this is the terrestrial laser scanner. Well, some company, they actually offer the options that you can put their terrestrial laser scanner and program it so it can be used as a mobile laser scanner. And these are the more dedicated systems. So I'm sorry, it's more dedicated systems, okay? Like that, it's more integrated system, okay? Or you can also put it on a train track, okay? As long as where you can put it, okay? So the result is like city blocks. You can drive through a city or a rural area or even a mountain road, okay? Even mountain road. So if you drive through a city, you can see a lot of things can be measured, or because the data has been collected already. So you can see all the poles. Sorry. You can see all the poles, okay, and all the cables, okay, all the cables, and you can see the landmarks, okay. So in Taiwan, for myself, now the autonomous car is a big topic. So the governments, they built this site as a test site for autonomous car. And for autonomous car, we have a term called high definition map. Okay, we want to create high definition map for autonomous car. That means we want all the lanes, the information of all the lanes, the information of all the parkings and all the light poles, all the traffic lights, all the signs, everything being mapped. Okay, so for this, we use mobile laser scanner to measure this. Okay, so this is the point cloud of that in a sparse version. The dense version is like that. So this is the dense version of the point clouds. So what you can see is black and white because it's just single wavelength laser. And with the intensity, you see all the markings and all the light poles. And so is this, okay? So with all these measured in 3D, so we can easily digitize all the lines, all the markings, everything, okay? All right, so this idea can be pushed, the mobile laser scanner, this idea can be pushed further, is that we can make it a backpack, okay? So we have a person carry this system, this this single laser scanner here. Other companies, they have other design, okay? You can see there are a lot of designs, okay? And so you can put this system everywhere you want to be, okay? Into the woods. Okay, so this will be the example results. So this is the example why you maybe want to have this mobile system on your backpack, because you can imagine if you want to measure in the woods, a traverse laser scanner, you will have to scan multiple times in order to get a complete scan of the area. But with this mobile system on your backpack, it's supposedly be easier to do the scanning, and that's the tracks conducted by the surveyor on the ground. Okay, and the other example will be like a construction site. Okay, there are just so many obstructions. You will want to scan from all directions in order to eliminate the obstruction of the line site. Okay. All right. This is my final slide. Actually, let me to. Okay, so this is a commercial mobile scanner system. Interesting to watch is that they are scanning a mansion, a very large building. Okay, let me get to a time. A very large building, so and many rooms. So if you want to scan this area with this backpack, so it's actually convenient to walk through. And that system can turn into handheld, so you can walk through this narrow corridor in this building, and you can scan in each room. Okay, so as a result, okay, let me see. So as a result is you scan this section by section, floor by floor, then you can get a complete scan of this structure, of this object of your interest. Okay. All right, so that's all for today for my lecture. So do you have any questions? Feel free to ask. Let me see. Okay, let me try to answer this. So Tong Bin Min, what software could we use to process a LiDAR image? Would you mind revealing the name of the software you currently use? Thank you. Okay, I imagine you are asking for ground. Wait a minute. You are okay. Let's see. Okay, let me just give you some names. Okay. Cloud Compare is one of it. It's a free software. Okay, it's a free software, but a little bit tricky to use for large project. Okay, but for small data set, it's actually quite good. Okay, Cloud Compare is one thing I would suggest. It's totally free. For commercial software, what I use is LP360. I find it easy to use for myself, especially I like straightforward control of the software. It integrates very well with ArcGIS. Okay, so but then this means you need to have ArcGIS license, and then you need to have LP360 license. So that's actually cost some money for you. Okay, or QTM. Sorry, QTM quick terrain. Why is it not okay? Beta version. Quick terrain modeler. It has a viewer version and also a full version. Well, I'm sorry, I cannot. what's going on? Okay. Well, anyway, so this is the, yeah, okay. So QTN is a visualization, okay? And if you are really ambitious, if you are more ambitious, this is the quick Terra scan. Terra scan. Okay. Terra scan. This is the software that a surveying company will use. Very, very powerful. Can do a lot of things. But I have to say, for myself, very difficult to use because it is for data producer to use. I am personally more like a data user. I'm not data producer. Okay, like the difference is that it can with the software from TerraSolid, you can do this. Okay, that means you can do stripe adjustment. Okay, so that's a very big difference there. Okay, I hope this is enough for you. But if you actually one more thing. Oh, actually, ArcGIS LiDAR dataset. LiDAR dataset. ArcGIS has an extension called LiDAR dataset. So ArcGIS can help you do this. But I have to say, awkward for me to use ArcGIS. Not very straightforward. Okay. And one more thing, if you can do programming, LiDAR. Okay, sorry. Maybe this is enough for you. It's an airborne LiDAR data manipulation and visualization for forestry applications. Okay, it has that. Well, actually, let me see if I can spell this correctly. Whitebox tool. Whitebox tool is another very useful thing here. Whitebox tool. Okay. I'm not sure about it's free or commercial. It is changing a little bit now. Okay, but you can try. Give it a try. Okay, very good, very good. Oh, I'm sorry. The other thing, if I can remember the name correctly, last tools. Okay, last tools. Yes, I think this is the last thing I like to share. Last tools. I'm not sure about if you can buy this software anymore, because okay, you can buy the software still, because the founder of the software, he deceased a few months ago. So everything is now back to service. So last tool, yes, you can try last tools. It gives you some capabilities that you can use it to process very large data sets. Okay. So yeah, I'm not sure I'm not sure what kind of project you are facing, but these are the options I can come up with very shortly. So hopefully this is useful for you.
Yes, thank you, Professor.
Yeah, sure.
Yeah.
Hey, where's my? Okay, and then for Joe. Is night better for LiDAR work due to low and lower ambient light? Oh, I think you are experienced person. You are a professional. Yes, it is. Yes. Yes, because sun is giving noise to the sensor. So if you can fly LiDAR during the night, go ahead and do it. But practically, for my LiDAR career for this 20 years, well, because I also get my PhD in LiDAR. No one ever do this. They never really do this because your airplane has to have proper equipment to fly during the night. And the pilot usually doesn't want to fly in the night, especially you are scanning in the mountains or hilly terrain, and you're asking them to fly as low as they can be. They don't like it. The pilots, they don't like it. So yeah, so I'm telling you, theoretically, this is what we want to do. We fly during the night, but practically, the pilot, they don't like it. All right. And the other question is, has LiDAR been used to inspect railroad track or base damage? For this one, my experience is that because the railroad, the inspection of railroad track, if you want to inspect that, actually you are looking at millimeter accuracy. You are looking for millimeter accuracy, so you can find the damage, such as damage on the track or something like that. For my understanding, if you scan on the railroad, actually you are scanning the poles, the lines, and everything. It's just like an inventory. It's like inventory kind of surveying or scanning. It's not like a damaging scanning. If you want to scan the damage on the rail, you will use another kind of LiDAR, okay? Another very specific line scanner. They are the kind of, it's a line scanner. They're on the order of micrometer. They're on the order, their accuracy is on the order of micrometer because that's the requirement of inspection, okay? Another question, in a deserted urban environment, can LiDAR be used to detect individual person's motion? If you are talking about airborne LiDAR, no. But if you are talking about other kind of LiDAR, yes. Actually, I would say, I think you are talking about, okay, might as well just show you this. I think you are talking about paradigm something. I think you guys are talking about, sorry about the commercial. I think you guys are talking about something like this. Okay. This is another kind of LiDAR. This kind of LiDAR. It has 64 lines being transmitted. So 64 laser beams being transmitted out simultaneously. So you can imagine it's spinning. It's spinning 64 lines at the same time. So with that, yeah, I think you can see there's a person. Okay, so it doesn't to be deserted. Okay, a lot of possibilities can be achieved with LiDAR, but then you need to have a clear application or clear goal, so you can choose the proper kind of LiDAR to use. Okay. Okay, so for Connie, is there any free LiDAR data set that we can use to learn about LiDAR? Oh yeah, yes, there are free LiDAR set. open LiDAR data. Open LiDAR data. Open topography. Okay, open topography. Okay. Most of the LiDAR, I think, in here is from United States. You get some from you will get some from Japan and the rest of the world. Yeah, and actually from Europe, you get some example from Europe as well. Okay. And Chou, again, I was thinking urban warfare in Ukraine, how to find hidden enemies location. Well, I don't think LiDAR is too useful for this case, I have to say. In my thinking, I think it's not. Well, I would think heat source, heat imaging system is easier to use than LiDAR, I think. All right. Okay. So I've answered all the questions, and I think the time is 6 o'clock. So that's about it. And thank you for coming to this lecture. I will return the lecture to Yang, to Mr. Yang.
Okay, thanks for Professor Huang.
Thank you.
Thank you. And let me show my screen. Hey, everyone, please write down your answer to this Google form.